It is estimated that during the next 50 years, the world's population will double and consequently energy demand will triple. At the same time, our main source of energy, fossil fuels, coal, oil, and natural gas, will be depleted. Renewable energy sources like solar, wind, and biomass can help, but they are geographically limited, climate-dependent, and unable to meet the energy demands of a populous and industrialized world. One of the options available now is nuclear energy. There are two ways of obtaining nuclear energy, namely fission and fusion. Nuclear fission suffers from negative public perceptions. Some of the primary concerns in the harnessing of nuclear energy are harmful radiations, radioactive waste disposal, and the threat of weapon-grade nuclear materials. Fusion is perhaps the best option for a truly sustainable long-term energy source. Fusion will be environmentally friendly since it does not release atmospheric pollutants that might contribute to global warming. Since the required raw materials, deuterium and tritium, are in abundance in the sun, fusion is capable of producing the energy that future generations require. The sun and other stars are powered by fusion. Harnessing the energy from this type of reaction presents great challenges to scientists and engineers. Steady progress has been made, but several scientific and technological advances are necessary before the dream of commercially producing electricity from this reaction can be realized. Introduction to Nuclear Reaction 2. In this lesson, you will learn to understand the processes of nuclear fission and fusion. Understand the occurrence of fission and fusion in terms of binding energy per nucleon. Explain the conditions for a chain reaction to occur. Understand a controlled fission process in a reactor. Describe a nuclear fusion process which occurs in the sun. The first evidence of nuclear fission was observed in the late 1930s by two German scientists, Otto Hahn and Fritz Strassmann. In their experiment to study the effect of firing neutrons at some uranium compounds, they discovered that the uranium nucleus had split into two fragments of about equal masses. The interpretation of this discovery as a fission reaction was worked out together with Lise Meitner and Otto Fritsch. Further experiments showed that uranium-235 fission yielded an enormous amount of energy, and each fission also yielded at least 2 neutrons. From this, they realized that a chain reaction would be possible with an unprecedented energy yield. The initial step in a typical fission reaction occurs when a slow neutron, also called thermal neutron, is absorbed by a uranium-235 nucleus. This increases the mass number of the nucleus by 1, producing a uranium-236 nucleus which is in an excited state. The uranium-236 nucleus is highly unstable and splits into 2 fragments almost instantaneously. In addition, some neutrons are also released. Click the play button to observe the animation of the nuclear fission of uranium-235. However, the animation should not be taken too literally. Click the Sequence button to reveal the sequence of a fission reaction. Click the Equation button to reveal the equation for this fission reaction. Note that the fission reaction involving uranium-235 splitting into krypton and barium is not unique. Other outcomes are also possible. Click the Other Possible Outcomes button. Fission resulting from neutron absorption is called induced fission. Some nuclides can also undergo spontaneous fission without initial neutron absorption, but this is quite rare. In a nuclear fusion reaction, two or more light nuclides come together or fuse to form a larger nuclide and energy is released. Click the play button to see the deuterium-tritium fusion reaction. Click the equation button to see the equation of the deuterium-tritium fusion reaction. When a deuterium nucleus and a tritium nucleus fuse, a helium nucleus and a neutron are formed. The difference in the total mass of the initial nuclides and the total mass of the final products is transformed into energy. This reaction yields 17.6 mega-electron volts of energy, but requires a temperature of approximately 40 million kelvins to overcome the Coulomb barrier, the repulsion caused by the positive charges. Summary. In nuclear fission, a large nucleus splits into two nuclides of almost equal size with emission of neutrons and energy. Fission resulting from neutron absorption is called induced fission. Some nuclides can undergo spontaneous fission without initial neutron absorption. In a nuclear fusion reaction, two or more light nuclides come together or fuse to form a larger nucleus. The occurrence of nuclear fission and fusion can be explained in terms of the binding energy per nucleon, which is the binding energy of a nucleus divided by the number of nucleons in it. Click the graph button to see the variation of binding energy per nucleon with mass number. Nuclei with high binding energy per nucleon are very difficult to break up. Isotopes of the iron group have the highest binding energy per nucleon and hence are the most tightly bound nuclei. Iron 56 has binding energy per nucleon of 8.6 mega-electron volt, which is exceeded only by iron 58 and nickel 62. This explains why there is an abundance of the iron group elements in the universe. Click the iron group button to show the position of the iron group elements in the graph. Nuclides near the iron group with mass number A between 40 and 80 are stable as they have relatively high binding energy per nucleon. This means that a great amount of energy is needed to break up these nuclides. Click the Stable Nuclides button. Nuclides to the left and right of the iron group have lower binding energy per nucleon and are less tightly bound. Thus, less energy per nucleon is required to break them apart. The left part of the curve suggests that a pair of light nuclides can be combined to form a single heavier nuclide that lies nearer the iron group to achieve higher stability. Such a process called fusion occurs naturally in stars. energy is released during such process. Click the fusion button to reveal the part of the curve where fusion occurs. The right part of the curve suggests that if a heavy nuclide were to be split into two nuclides that lie near the ion group, the resulting nuclides would be more tightly bound. Such a process is called fission, and it involves the release of tremendous amount of energy. Click the fission button to reveal the part of the curve where fission occurs. Summary: nuclides around the ion group with mass number between 40 and 80 are stable as they have relatively high binding energy per nucleon. Light nuclides have low binding energy per nucleon and can be combined to form a single heavier nuclide to achieve higher stability. A heavy nuclide also has lower binding energy per nucleon and can split into two nuclides that lie near the ion group for higher stability. From the binding energy per nucleon curve, we can see that the left part of the curve has a much steeper gradient compared to the right part of the curve. Thus, it is clear that more energy per nucleon is released in the nuclear fusion than that released in the nuclear fission. The energy released by fission of a high-mass nuclide can be estimated by considering the total binding energy of the nuclides before and after the fission. Energy released equals total final binding energy minus total initial binding energy. Assume that a high-mass nuclide such as uranium-236 splits into two equal fragments, each of mass number 118. From the curve, estimate the binding energy per nucleon of uranium-236 and its fission fragments. Answer: the binding energy per nucleon of uranium-236 is about 7.6 MeV and that of its fission fragments is about 8.6 MeV. Click the fission button to see how the total energy released by fission of a uranium-236 nucleus can be estimated. Similarly, the energy released in a single fusion process can be estimated. Consider two light nuclides, each of mass number 5, combining to form a single nuclide of mass number 10. From the binding energy curve, estimate the binding energy per nucleon of the original nuclei and that of the fusion product. Answer: about 2 MeV and 7 MeV respectively. Click the fusion button to see how the fusion energy released is estimated. By considering the amount of energy released per nucleon, nuclear fusion can produce about 5 times the amount of energy produced by fission. Summary: energy released equals total final binding energy minus total initial binding energy. More energy per nucleon is released in a nuclear fusion than that released in a nuclear fission.